gentlemen, welcome to our Computer Science Colloquium. Next week, if you're wondering what's happening next week, Wendy Bartlett from Hewlett Packard will be here, and she will be talking about fault-tolerant computing. And just to give you a little bit of very quick stop here, she started her career in IBM, went to a company called Tandem, and that's where the fault-tolerant computing comes from. And now she's at Hewlett Packard, so that's next week. This week, I'm very delighted to introduce to you, number one, it's not just one, you get two for the price of one today. Vicki and Dave Shreiner, who internationally are well known as Mr. and Mrs. OpenGL. I don't know why. Today we are going to talk about something in your pocket, mobile computing, whatever it is. Exciting. So let's welcome them.
Hi. I'm sorry. Oh, don't tell me you were married. It's a problem when you get spouses actually giving presentations together. So, anyways, yeah, fault-tolerant computing. Don't miss that. So, I talk about Blitz and Glam, more or less, or, well, okay. Here's the motivation for this. And just a little background about myself. I've been working with OpenGL since 1992. So, a few of you in the audience were actually born and cognizant at that point. Most of the rest of us like, So, I'm also the author of the OpenGL Programming Guide, the Red Book that you might have seen. How many of you have actually used OpenGL? How many of you have heard X? Okay, are you just being shy, or are you just like, oh, no, I'm not going to tell you OpenGL here? Really, it's okay. So, I'm author of that book. I'm also author of another book called the OpenGL ES 2.0 Programming Guide. There's a lot of OpenGL that happens in our house. Cat even knows how to do it. But what I'm here to talk about, so Vicki still works at Silicon Graphics, where OpenGL began. And I used to work there for a long time. She now worked there longer than I did. But they divested themselves of the part that I worked on. And so I now work for a little company called ARM, which pretty much very few people have ever heard of. Anyone actually heard of ARM? You know what they do? Yeah.
What do they do?
Make chips, processors.
Darn close.
They design them.
Design them.
Yes, yes. Congratulations. You win the big prize of absolutely nothing.
Oh, we should run by.
Yeah, we should have. That's better percentage than most people who, they've never heard of this, but almost, how many of you have mobile phones? Right? With the exception of maybe one person's hand, every mobile phone in here has at least one ARM port. This little baby here, right, of course this is an iPhone, has 7 ARM cores inside it. So there's tons of computational power that's inside of there. And what's nice about this one is this really rocked the world in the fact that it was the first one to take a mobile GPU and actually use it inside of the phone. Like for example, if you have a Motorola Razr, it has a full-blown graphics chip in it, but no one ever enabled the software to use any parts of it. So what this talk is going to be a little bit about is what's coming down the pipeline. And what's coming down the pipeline actually is very interesting, in fact. I know people have some laptops inside here, and actually I'm kind of betting my career on the fact that the mobile technology that you're seeing here is going to come up. It's a very ultra-light mobile laptops that have full-blown graphics capabilities that are coming, right? The same kind of things you see in the desktop GPU, but with needing to strap a car battery to your back to be able to power it for 3 hours. So that's kind of our motivation for this part. Now, this is kind of draining the roost at the moment. Now, there are 2 reasons why this is good. One, they actually bothered to turn on the graphics processor inside of it. And so everything you see on an iPhone is all OpenGL. In fact, it's almost identical to what you have in the desktop of a Mac. See one happy Mac user here. He's very slow. A second happy Mac user behind a camera. You're recording this for posterity's sake. Good Lord. So those guys are very good about doing lots of interesting things with OpenGL. Right? All the effects that you see on the screen are actually OpenGL effects. They've taken and leveraged it quite well. Now, this device has a very different GPU in it than you would find on the desktop, only in terms of performance. Most of the features that are there are identical to what you're used to. And actually, the programming API, which Vicki's going to talk a little bit about the differences, will come out that if you know how to do OpenGL, you're very well positioned to be able to program these kind of things. And from what I've seen, the biggest industry at the moment, Apple just opened this up so you can put applications of your own on top of it. Any of you actually pulled down the SDK? Any of you own iPhones, first off? And those of you who actually thought about trying to program? Yeah? Yeah, I'm very impressed. The biggest thing happening for them, I meet with Apple quite often, got such a unique user interface, and it also has a very powerful OpenGL interface to it. So you can do lots of really cool stuff. So what this guy uses is something called OpenGL ES 1.1. Vicki will tell you all about that. And what's going to be interesting is that's only the beginning. They got the first shot of the barrel. This is now about out in the market for a year and a half. The technology's been around for about 3 years to do this. The next generation will have all the features and programmability of regular OpenGL. So do you guys know what a shader is? You've heard about those, right? Next generation mobile phones will be shader programmable. You'll have a fragment shader, we have a vertex shader. Vicki will tell you all about those different things.
I don't need to now, but it's already
No, there are other differences. So those kind of devices will be hitting the market probably in about 18 months. It'll be very interesting to see how everything goes. So at that point, are you ready to take over?
So anyways, just to give you a little bit of history about OpenGL, because people still are using their laptops, their little tower PCs or whatever that have OpenGL on them. So that's still, you have the desktop flavor of OpenGL. The current version is 3.0. That just came out at SIGGRAPH this August. And maybe what didn't make as big a splash as it had tried to last year when they tried to come up with something. But the whole thing there is that it still has what's called fixed function, the fixed function pipeline, and it also has the programmable graphics stuff. So we're going to see a change early next year where the next flavor of OpenGL for the desktop will only be the programmable stuff. So they're kind of moving in that direction, and it's not, I mean, I hate to see it go because fixed function makes it easy to do certain things, but it's been around for 15 years or something, so it's, yeah, to kind of keep the dinosaur around means that even as you add new features, you still have to keep all those old features. And so the graphics card vendors like NVIDIA and ATI are complaining about having to keep all this old baggage when they want to be able to do new things. And so that's kind of the future. And right now, because they have both the fixed function and the programmable options in OpenGL 3.0, there's lots of different ways to do things. So somebody can go ahead and use sort of the standard fixed function pipeline way of creating their primitives, where they do GL begin, vertex, 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 and then GL end. Or you can do it with the shader stuff. So, you know, right now both things work. And one thing is, to me, the one thing from a teaching point of view, because I teach at SGI, I teach people how to use computer graphics, or in particular OpenGL, to do mostly defense applications. I'm not sure I want to say that. But anyway, since I opposed the war, anyway, let's get off that topic. Is that there's a lot of fixed function programs out there. And so that's the kind of hard thing right now, is if they're going to move to the new way, they're going to have to radically change their programs if they want to keep going. So I find that to be a little sad. And then OpenGL ES has been around for a while, and these are for the embedded systems, for these small cell phones, and you know, someday your toaster and your refrigerator and all that kind of stuff's going to have all kind of technology in it. Some of them have it already. So for OpenGL ES, they have two versions right now. 1.1, which is what the iPhone is using right now. And 2.0 is the new version that just came out. And it is, they chose to kind of compress things already, from rather than supporting everything that the desktop flavor of OpenGL has. Since there's multiple ways to do things, why have that? We just need one way, and we need the fastest way, or the simplest way. So that's what they chose here. So they did take some of the functionality out. They have most of it, but it's only one way to do it. So they've already kind of cut it down. Yes. And so now if we just take a look at what was the fixed function pipeline for a moment, and then we see where it's going to go in the future with the programmable pipeline, you'll see on the right-hand side all these blue boxes. And basically we're going to move all of those blue boxes into your shader, and whether it's going to be the vertex shader or the fragment shader to do different functionality. So we'll see that in a moment. And all the stuff on the left here with these green boxes, these are the stuff that you set up this data. You give it vertices, you tell it if you're using lighting what the normals are for which direction and how much of that color it's going to get. If you're using texture mapping, you set up the texture coordinates and all of the different color pieces and all of the parameters that go with that. And if you're just using plain old color, then you just get to set up the RGB value and whether or not you're using flat or Garot shading for that. And so what we're going to see here then is that if we're drawing just a simple primitive here, like a triangle, I hope you can see that little sort of red dotted, red dashed line that goes through here. And these solid sort of white lines, these are your pixels. And so what you do normally is you would give it, in your GL begin, you give it your three vertices. So you give it this endpoint and that endpoint and that point. And then basically what we have to do here, the rasterizer, basically has to take the information those vertices and figure out which pieces it's going to use and what colors it's going to make them, and so where in space it's going to be, and also the color data and information about it, and again, texturing happening, things like that. So what happens is, we're going to see another slide that actually shows us these fragment tests, and if it passes all these fragment tests, then basically it's going to get into the frame buffer, and it'll be a pixel. If it doesn't pass one of those fragment tests, then it's gone. And so the whole thing about the fixed function is this, you can't change the way this order goes. It's the whole fixed area. So anyway, this fragment wants to become a pixel and be in the frame buffer, but depending on where it is, it may not. So, fancy little things. So what happens here is, kind of looks a little funny, that triangle, how it would actually look, because there's pieces over here that don't actually end up being part of the triangle. Now, this would also be if we did not have anti-aliasing turned on. Okay, so it looks like a very blocky, I'm not even sure triangle. But what happens is, part of what has to happen is the rasterizer has to figure out whether or not that pixel belongs as part of the primitive. And so it's a very simple test of, does it hit the center of that pixel? And so you can see here, this doesn't hit the center. So it's not considered part of it. So even though we look at it and the line goes through there and it looks like it should be part of it, fails that part of the test and therefore it's not in there. So if we're doing anti-aliasing, where you're going to take sort of the corner cases of these pixels and you would say, okay, well he doesn't touch it, but it's pretty close. So we're going to use some percentage of what would have been this color, the blue, with whatever color is behind him. And so you would come up with this combination of blending and stuff. So then you're going to get more of your triangular shape or whatever. All right. So now what we have here then is, on the right-hand side, we would have choices. I didn't tell you before, but the darker blue boxes in that previous one were things you would turn on and off. And the lighter blue ones were things that always happen. And so here, I mean, you don't have to do texture mapping. So if you don't turn texture mapping on, this one's not going to happen. Color sum is something else that you turn on if you decide to do it. And this is where if you're doing lighting and you're using texture mapping, then you would want your specular highlight color to happen after the texture mapping, so you don't lose it. It's the more complicated piece that has to be calculated in lighting for that color computation. So you don't want to lose any of that information. And then fog, if you were going to enter fog, you'd have to turn that on. But basically what you're going to get here are, whether you're drawing points, lines, or triangles, primitives, they're going to go through any of these things that would change their colors, color information, and then basically go on to the fragment tests. And so that's what I'm saying. If they don't pass one of those, they're not going to make it into the frame buffer. And so then this is the fragment test that we have to go through. So the pixel ownership, this one has to do with whether or not, and this one always happens, it's like blue one, whether or not you're going to be seen. So you have this concept of what's called a viewport in OpenGL, and that's where you would normally draw. But there's some tricks you can do. You can make your viewport bigger than your actual window. And then it's whether or not it's going to see it, whether OpenGL thinks it's going to see it, so it'll go on and continue to do some tests. And then scissor test, whether or not, again, you can make some choices about whether or not things are visible. Alpha test, whether or not things are solid color, or they're going to be somewhat see-through. So if we're doing some of the blending and anti-aliasing and stuff. Stencil test, another set of buffers that we can do things. So if you have cockpits, little round, speedometers and things or whatever they are, you can't have round windows, but you can actually make stencil buffers, or used to be overlay, underlay buffers with different shapes, and then you can say whether or not you can see through it or not see through it. So you can make like your wood grain for your cockpit or whatever. Depth buffer test or Z buffer test, certainly something that is used a lot, so that the system gets to figure out if something's in front of or behind something versus us having to figure that out all the time. If you're drawing static objects, that's easy. Then you can do it. But if things are moving, it becomes more complicated, and you just might rather have the system do it for you. Blending, like I said, sometimes used with alpha stuff, but doesn't have to be. So blending used with anti-aliasing, and if you want to merge colors, somewhat see-through, glass kind of stuff. Dithering, an ancient method, not really worth talking about, but it was a way for color stuff. And somebody obviously knows about it, so. And then logical operations, any kind of mathematical operations and things can actually be done. Because in the end, all we're trying to get is a color for a pixel. And those color computations, they're all equations. They're just math formulas. So it doesn't really matter whether it makes sense logically, but we can just do all kinds of math formulas to come up with color in the end. side here, you're going to see these green boxes again, but you're no longer going to see the word color, the word texture, the word lighting normals. They're just called vertex attributes. This is just data. It's any kind of data you want to pass me to finally figure out what's going to come out the other side. And then this big square in the middle here is where all those light blue and dark blue boxes were. And all of that is now yours. You get to figure out what to do. So I guess that's exciting if you want it to be exciting, and I guess it's also tedious if you like some of the other functionality that was done for you. Because now it's everything you have to do yourself. You can't just choose one little small piece that you want to do yourself. So you have to do it all yourself. But basically, once it comes out the other side here, this vertex shader, basically what the rasterizer needs, it's still going to be rasterized after this, you need a point space, and then you need some kind of color information or whatever to go with it so it can figure things out. So that's still going to happen. And then we're going to deal with the fragment shader, and that's actually where you would set up any of your color information. And so we still have our rasterization here. Does it fall inside of our drawing area in our window, and are we going to see it? So can I care about it? And, but again, big box there for you to do whatever you like. And you can do whatever you like with it. It doesn't have to just be color calculations. But this is where it would have been your texture, your color sum for the specular highlight, color for lighting, and if you were doing fog or something, those calculations are what now would be in here. But again, you can do whatever you want to come up with the final color or whatever for that point in space if it ends up in its rainbow. And that's yours.
It's fine. This took me years to be able to catch up with the rate that Vicki talks like that. That's okay. So,
I'm from the East Coast, sorry. I tend to talk a little faster on that side of the coast.
I'm from the East Coast too, but
You're from Pennsylvania. Okay, when you're married 15 years, it's okay.
yeah. Right. So Vicki just talked about both the fixed function pipeline and the programmable pipeline. So presumably, how many of you do not possess a computer in your home that has a graphics card? Good. See, I'm helping you because I know you don't want to fall asleep, and it's tough to raise your arm. Okay. Right. So in a desktop environment, just out of curiosity, how many of you got NVIDIA cards? How many got ATI cards? No. Actually, my personal opinion, and it can be reported, I think ATI has better hardware. I think NVIDIA has a better software driver. The problem is, right, everyone sees how the software interacts. Yeah. Conceptually, both companies chase me like crazy to work for them. I'll work for neither of them. But if I had to choose, I think I'd work for ATI better. Anyways, just a nice report in mind. Yeah, someday somebody from NVIDIA is going to kick me really hard. Okay, well anyways, so what happens here? You've got all those pipelines. Now, the important thing is, in the iPhone, for example, you've got one of those fixed function pipelines inside. All the features that you're used to, lighting, texture mapping, multi-texture for that matter, all those kind of features are present. But this is going to kind of change some things, right? Because let me cast it this way. Inside of a desktop system, we have all the things we could ever want, right? If you're NVIDIA, you go, you need a kilowatt power supply. Yeah, that's more than your toaster uses, right? There was an odd chart I saw from Intel, the Itanium, which is a kind of big horsepower chip that they used to do for supercomputing, right? Generated more watts per square centimeter than a nuclear reactor. Now, the funny thing is, you get something from a nuclear reactor. You didn't get much from an Itanium chip. But be that as it may, this is clearly not going to work for a mobile environment, right? Other things we've got. Well, in a mobile phone, we don't have unlimited power. We've got very fast wide buses, right? You've got PCI Express, which runs 2 gigabytes a second. It takes a lot of juice to wiggle those wires that fast. Flat out, statement of fact, right? We have virtually infinite silicon area. When you look at the size of, if you can see past the heatsink on your NVIDIA card, right? The silicon is this big, right? That's a lot of metal, sand, and paper clips. Just no two ways about it. Now, if you think about something this big, tell me a cell phone is that big. Even the iPhone is not that big, right? And so there's some trade-offs they have to make about, you've got to get this smaller. And there's something that comes from the mobile side about what people who design these things really are concerned with. Performance is somewhere in the mix, but trust me, it's not first and second. Something else that's there, we have lots of memory. If you think about, for example, any of you run your graphics cards in dual monitor mode? So dual monitor mode, probably running, 1600 by 1200, twice that size, 3200 by 1200. If you do 24 bits or 32 bits per pixel, plus a depth buffer, plus a stencil buffer, you're talking about a couple of megabytes of memory. You don't think anything of it because you slam a couple of DIMMs inside of it, right? iPhone, 16 gigabytes. Got to hold, well, you know, your current, what are those things called? Little vloggy, the iPod video games. What's that? Podcast, thank you. Just slipped my mind. I was learning too much uranium when I was a kid. I grew up by 3 Mile, long story. You got all that stuff in there. You have to run the operating system. You have to have space for the frame buffer and all those things, right? Having dedicated memory for this just doesn't fit into the mantra of a mobile device. However, as you're going to come to find, mobile devices are becoming extremely powerful. And for any of you who aspire to be business people who fly around on planes and give PowerPoint presentations, anybody? Anybody? Why? There's one poor lady in the back who looks unhappy, nodding her head going, yeah, this is your life?
It has been.
Yes, it's marvelous. Nothing better than airline food. Right. Anyways, we're working hard to relieve you of the 8-pound problem that you carry around that is a laptop. And for the most part, it's my personal belief, these mobile devices will become far powerful enough to do everything you want to do. I'll get in there in just a second. Why does it work? I really want this to be a technical talk, so the design goals for the desktop space is to maximize performance, screw everything else, right? Your electricity bill can go up, we don't care, we're not paying. So you can do whatever. And we want the richest feature set. We'll support everything DirectX 11 has inside of it, even when most people don't understand what a Hall shader is for. Go read it in the book. So, how does this affect their design? Well, right, when you're playing games, one of the worst things that can happen is you move the joystick in the game and the character doesn't respond, right? This is a concept called latency. And in order to do computer graphics, you want to minimize latency in the system. So it turns out most desktop systems are what are called immediate mode rendering systems. Now, whether you do DirectX or whether you do OpenGL, right, you sling a triangle down the system, and that triangle appears on the screen as fast as it can be processed. Now, there's really good things about that, right? If you have a really honking CPU, you have a fast graphics card, the latency between when you issue the command and when the pixels are all lit up and finally processed is a very short period of time. The problem is, in the immediate mode rendering system, it's kind of fire and forget. Once that triangle has been rasterized, all the information about it is done. So this makes it kind of difficult if you want to do, say, occlusion testing. Is this object in front of some other object? So, since I'd like things to be interactive, how do we actually solve this problem in computer graphics? You must have learned about this. Did they, George? Okay. George passed the test. Anyone else? Come on. It's that last letter, the alphabet thing? Yeah, I work with a lot of Brits. They say, oh, the Z buffer. Oh, yeah, I did South Africans, Australians, Kiwis. Anyways, right? The depth buffer, sorry? Kiwis? Yeah, they even call themselves that. They do. So the depth buffer is a little way that we keep notes on a per pixel basis on what was actually closest to us. The problem with this is we need to keep that information per pixel. So in a desktop system, right, we have all the colors in the frame buffer. And because it's double buffered, usually we have 2 of those. Then we have a depth buffer, keeps some information. And then you want to do some extra special things. Occasionally you need additional notes, like am I inside of something or outside of something? Or you look at winding lists. This extra buffer called the stencil buffer, cover that in costume? Right? The stencil buffer is used for keeping additional notes about 3-dimensional objects. Well, classically, am I inside of something so I can do constructive solid geometry? Why do we have to do this? Because we've chucked away all the information. You send it down as a triangle and some extra information. And then you have to do all this odd stuff to remember it around. And, well, you can do all these things. They're very well-established techniques. And they map really well into doing low-latency graphic systems. Modern ray tracing, as long as you don't talk to the zealots, still is not a real-time method of doing this. Right? Ray tracing, you look at the... I'm glad you're amused. Ray tracing, you remember the entire scene and you work on a per pixel at a time. But since you have all the information there, you can do tremendous amounts of things. You can do reflections, and you can do transparency correctly, and you can cast shadows, and all this stuff just immediately falls out. The problem is, ray tracing is an unbounded problem. Just keep chucking mirrored spheres into your scene and see what happens to your CPU. Right? You've got to learn to enjoy wine and enter retirement before you're finished. Right? Just 2 mirrored spheres and point the vectors at each other, and you'll be there for a long time. Nonetheless, rasterization, we do things slightly different. Now, how exactly does rasterization work? Well, I covered most of it, but we fire it down there, and when we go through the pipeline, if you remember the slides that Vicki showed you, we compute the color of a fragment, right? By first we do the vertex shader, plop it down on the screen. We run the fragment shader for all the rasterized pixels. We get the color out the other side, and then we do this visibility testing. So then we do the depth buffer test and determine if you can see everything. Well, the problem is, in classic old-style stuff, by the way, we're both voting fixed fixed function and like selection. We like the old way of doing things, but
But we lost.
long story on that one. Anyways, we keep pushing fixed function because it's very efficient for getting things done. Any of you like begin end? Any of you actually been exposed to GL begin, GL end?
How did you begin and your vertex, right?
It's simple. Okay, anybody want to draw 3 coordinate axes to know where the origin is? Yeah, set up a draw race. See how much fun you get with that. Right, it's just a lot more work. I can tell you stories that just embarrass people. I'm not going to bother. Trust me, a lot of people who want to kill immediate mode love it as well. They just have a public face and private face. The point is, right, it used to be the case that there wasn't a whole lot of shading that was going on. Right? We compute some colors, we apply a single texture, we get a fragment on the other side. But then somebody said, you know, this is lazy. Let's do multiple textures per fragment. And, well, what the heck? We'll open it up, let you program it, and write an open-ended fragment shader to compute all this massive work. So you can apply, 16 textures to it. You can do font-based lighting. You can do all sorts of things. You can do a little ray tracing in the fragment shader. You do a ton of work here. And you go, oh, I failed the sequence test. And all that work goes away. That's why you need a kilowatt power supply and a bus this big, because you're not really doing things the way you really should be. So, immediate mode renderers, right? Presumably, do you make them write rasterizers anymore? No. Yeah, actually, it's kind of funny. I would have said about 5 years ago, knowing how to write a rasterizer is something you never have to do again. Oddly enough, I'm wrong, right? Because now, people are buying the company I work for. And SGI is more of a big computer system, right? So they just buy parts and put them in together. But the group I work for is well pointed out. We don't actually make processors. We make the stuff that goes into processors. So when you buy $1 million product from us, we give you a CD and spine. But it's the hardware design for some part, whether it's a CPU or GPU or memory or anything along those lines. It turns out that this is becoming very big business because anybody who connects to a screen is going to want a GPU. Screens are getting bigger in geometry. And anyone who does actually makes chips will go out and buy this stuff up. And there are a lot of people who are making graphics cores. And the big thing about graphics cores is actually knowing how to write a rasterizer, because that's tough. And so lots of companies are popping up. In the last 5 years, 6 companies popped up to write rasterizers. Before that, there were 2. There was NVIDIA and ATI. NVIDIA and ATI snatched up a bunch, a couple others standalone. There actually is an industry. Another one popped up in the last 12 months. And there are other people doing this themselves. Please.
I just am interested in vector graphics. How does that relate as far as raster graphics in your industry? Is it a lot less
Excellent.
analytical, or is it more research? Or
No. Well, so vector graphics preceded the rasterization part, right? So if you go in the Wayback Machine with George and myself, before they had frame buffers, which were broken down into pixels, the original display devices were like your old style television, right? Not plasmas, but like the old LCD screens, where there's an electron beam that would go around. For modern televisions, there's a fixed pattern, but you used to be able to control the electron beam by controlling the magnetics. And you would draw perfectly smooth vector graphics that way. So that was actually the first bit, because people would get CRTs and they couldn't afford the memory for a frame buffer. That went by the wayside because rasterization is a really easy implementation to accelerate hardware. The problem is, for most of what humans want to work with, vector graphics are what they are, right? So vector graphics manifest themselves as fonts. If you use like Photoshop or Adobe Illustrator, those are all vector-based APIs. Flash, SVG, and actually a lot of stuff that goes into web browsers. So it's turned out that vector graphics really has had a resurgence over top of GL. In fact, so major aside, but OpenGL is controlled by this thing called the Kronos group. And the Kronos group is the one who's specifying pretty much all the graphics APIs, aside from the ones that Microsoft has done. And oddly enough, Microsoft has even adopted a few Kronos APIs, but completely different issue. There are 2 primary APIs. There's OpenGL and there's OpenVG. And VG is the vector-based ones. So if you say, I want to draw a font, or more specifically a glyph from a font, right, so the letter A, normally they describe those as Bezier curves and connected things. And it's a huge problem to actually be able to do that fast. If you have a rasterization-based machine, everything I'll talk about, with your NVIDIA or ATI cards, they actually have to take those letters, tessellate them into triangles, and if you think about it, as you project those curves onto a screen space, you need to control the tessellation, and this is hugely CPU style. Now, geometry shaders show some promise. Do you know what geometry shaders are? Ever heard of them? No. Geometry shaders are something we didn't talk about at all in the OpenGL pipeline, because it's not officially there yet. But after you do the vertex shading, which basically takes and transforms your vertices from 3D space down into the screen, you can run geometry shader to basically say, here's a triangle, break it up into more triangles, and basically generate geometry down in the card. So that shows a little promise in doing the vector stuff. But vector-based APIs and actually rasterizing them well is a really tough problem. And people have a lot of difficulty doing it well fast. And oddly enough, in the mobile space, it turns out that this is huge. Right? The screen resolutions are going up. You want to be able to talk, make a mobile phone that works around the world. We're easy. We get 26 letters in our alphabet. Right? Kanji 50,000 in the primary alphabet plus another 7,000 in the other ones. You don't have enough memory to store all these things. Right? And if you do them as bitmaps, that's a mess. So the answer is people are clamoring about this all the time. Actually makes my job very difficult because I'm a GL guy. Yeah, use triangles. We're like, nah, we want this stuff. So if you learn about vector graphics, mouse algorithms, the world's your oyster. So anyways, back into our regularly scheduled program. I got 15 minutes and 15 slides. Fuck your seatbelts. Okay. Medium mode rendering. This is how all of you've written your basic while loop. So if you program glut, right? The glut main loop is this for each on the outside, and your display basically is what happens inside of it. What do you do inside of your program? You change some state. You change the material, change the color, bind some textures, anything along those lines. Roughly, you set the state, and then you look for every pixel that's in a primitive. Read rasterizer, right? We figure out what color to make that pixel based on that. And then we test to see whether it's visible. And if so, then we update the pixel in the frame buffer.
So is there any way to switch that so it goes more like if pixel is update, visible, update, shade, pixel state?
Have you been reading ahead? Oh, okay. Hold tight because maybe. There's a reason they don't let me in front of people. Don't make me professional. It would really be painful. Right. The answer to your question, sorry, to be kind of flippant. Absolutely. Not a new idea. People figured this out a long time ago. It's just that commercially viable products that do this have it difficult to get into the end marketplace. I'll explain more in just a second. So why do they do this? Well, right, as I talked about before, we want a low latency system. But for these guys, they require huge amounts of bandwidth. My favorite is talking about trilinearly bitmapped textures per pixel. Right? We do 8 memory reads because we have to pull in 8 texels. And remember, those are texels, so they have red, green, blue, and maybe even alphabet to go with them. Right? We'll write out the final pixel that goes along with it. We need to sum up the 8 values that we have, and well, we weight them by the pixel coverage across the pixel. You studied texture mapping somewhere, right? You studied filtering on that part. Blank stares. I'm sure you get there yet. Excellent. So when you do this, tell George, no, you got it all wrong. Actually, this can be done in 6 multiplications. It's not really difficult. It's the distributive rule that you learned in algebra in 7th grade. Nonetheless, if you look at this row, there's a lot of work to be done per pixel, and then we chuck it away because we failed the calculus. And if you imagine doing this for a lot of pixels in the screen, a lot of stuff. The long and short of it, just if you look at this particular chart, there's a lot of memory bandwidth that needs to be moved around. And if you have a lot of overlapping geometry that goes, which is going to have a lot of depth testing, you wind up doing a lot of work you throw away. Now, modern graphics cards do have an out in this. There's something called early Z column. So what they do is they basically keep track of what's the closest thing in the eyeball inside of the entire depth buffer. And if you draw something that's going to be farther away, what's the farthest distance? And if we can guarantee that all the pixels we're going to generate are farther than that, there's no point in even making them go through the process. So there are ways that people have accelerated this where they can throw away entire primitives at a time. But it requires you to write your software in a particular way to draw everything front to back, which, oddly enough, most of this generation's got. Draw front to back, good thing. Most of the previous generation that Vicki talks about is still doing back to front because that's the way you used to do stuff. So no, bad for the height. Okay, so how do we switch gears from doing this for a cell phone? Well, in cell phones, the design mantra is power, performance, and area. Minimize the power, right? You'd really be torqued if you're in Nintendo DS and you play it for 2 hours, right? They won't even taught you. Nintendo will not taught you unless you can guarantee 10 hours of performance out of the GPU on a battery, right? So this is huge thing. Area, right? You don't want to carry around an 8-pound Nintendo DS. It just isn't good for 3-year-olds, right? And performance, yeah, it's in there somewhere. Now, inside a mobile device, bandwidth equals power. So we don't have a 16-way PCI Express inside of these things. Sorry, just not going to get that. And even worse than that, your bus traffic is very expensive. So everything that can be done to keep things inside of the main application processor. Now, inside your cell phone is basically a computer on a chip. You have the main CPU, you have some chunk of memory, you'll have things like the radio for decoding the the audio signal that comes down for actually making a telephone call. Anyone still make telephone calls? Right. You've got to run the UI, so you're all used to icons and moving around through that, rendering the fonts, that's all inside of there. A bunch of things for noise cancellation, filtering, so you can actually sound like you're underwater, as compared to just completely screwing up the phone call like most of the old ones. And a bunch of other stuff, right? So now they play movies, so there's probably a video decoder inside. Oh yes, and there's that camera, and you probably want to do white balance and color correction, and maybe you want to do a movie, so you're going to have a movie encoder. It's a full-blown computer sitting inside of your cell phone. And you only want to pay $200 for it, and you want the battery to last for 7 days. Jeez. So, what happens in these devices? Well, we're stuck, right? We're restricted memory. Right? Most machines, if you don't think about the iPhones for a moment, most regular cell phones only have about 120 megs of memory. Right? Apple went off and they charged a premium, put 16 gigs in there and charged you $500. Trust me, the markups on those, good stuff. But, so, how does this actually affect doing graphics? We don't have space for a double buffer, well, 2 color buffers, a depth buffer, and a stencil buffer. Then you'd be tossing about 6 megabytes of memory out there to use one thing that probably isn't used that often. And probably doesn't need to be updated in the same way. Most of your time, things of your mobile devices are just certain user interface. Right? Okay, maybe you're playing some games, but even if you think about your general laptop, you're doing Word, you're doing Excel, browsing the web, doing PowerPoint, what's on the screen generally does not change at the same rate as an interactive 3D graphics game. So refreshing the entire frame buffer probably isn't something we want to do because, well, that would require bandwidth, we've already equated power, all bad things that happen. So the other parts, right? We also have large caches are a problem. Effectively, the frame buffers are cache, right? And so these are problems because if you want to stick it all in there, your silicon area gets big. So in these kind of devices, the constraints are really, really complicated. So, here's what we try to do. What if we can eliminate all the redundant computation? Defer expensive operations as long as possible, like doing shading after visibility, just as was pointed out by the gentleman in the back. Minimize the bus traffic, and do some other stuff. And what we arrive at would be something called deferred shading. Not a new idea. There's some really, really, really bright people who work at University of North Carolina, Chapel Hill, who made this system back in the late 80s, early 90s called Pixel Flow. It was a kind of box about yay big, and it was great. Super configurable, lots of boards in it, cranked out really beautiful pixels, really great stuff. Hewlett-Packard bought the project, productized it, and killed it after a year. No one bought it, which is kind of a sad thing. But they did all this kind of technology in it. It was fully programmable at that time. They did what was called deferred shading, and actually used something called a tiled rendering. This is where the big benefit comes in, and I'll show this in kind of an algorithmic slide in just a moment, in these mobile devices. So, you remember immediate mode rendering. We fire a primitive down, and it immediately hits the frame buffer. There's another way you can do it, which is kind of akin to ray tracing. You store up all the primitives in the scene, and then you basically work on little parts of the frame buffer at a time. We call them tiles. Figure out all the primitives that go inside of that tile, and then for each of those tiles, you know all the primitives inside of there, everything required to render them, and we just work on that little piece at a time. Now, the problem is, so I'll point out, it adds a little bit of latency, but it gets around almost all the problems we have. So you remember I talked about this huge box this big. Turns out that's going to be the latest technology you'll find hitting the shelves in about 2 years. Pixel Flow became a company called Power VR, which got bought by another company called Imagination Technologies, who actually are selling that exact piece of hardware now inside of a cell phone. It's amazing, 20 years ago. So, how does this look? Exactly as pointed out, what we do in this case is we record all the state changes for all the primitives. Or more specifically, all the drawing calls that happen. So you bunch up a bunch of triangles, you go off and draw them. We record the state that goes along with it. And then basically for every pixel in the frame buffer, or more specifically, because that's a lot of little tiny jobs to launch off, we break them down into little tiles. So grab 16 by 16 pixel or 32 by 32 whatever. And you look at all the primitives that are inside of there, and basically for all the primitives that intersect that pixel, figure out if it's visible. If so, set the state to that, and then go off and shape. Now, this is the holy grail. To be absolutely truthful, people still don't quite do it this way. And part of the problem is not so much technology. It's completely obvious how this algorithm works. The problem is somebody holds a patent for doing it, and so none of us want to infringe a patent. You all understand technology, IP, and patents. If you don't, yeah, it sucks. By the same token, most companies will pay you very, very well for making patents. So, write up patents, submit them, play the game. Anyways, most of the time we actually do stick the shading part a little bit farther up here and still the visibility, but we try to amortize the cost of this. But by doing just this part, every pixel in the frame buffer, more specifically, every tile, or every pixel in a tile, and then we put another loop that goes for every tile in the frame buffer, we're able to minimize the amount of frame buffer storage required. We still have a full depth buffer, we still have a full stencil buffer, we still have a full color buffer. It's just a little tiny piece. We figure out the final image for that and then write it out to where it's going to be scanned out. So it simplifies a lot of work. Now, there are a couple of things that happen inside of here. Everything that you issue from an OpenGL API standpoint needs to be preserved. So every time you change the color, bind a new texture, put in the shader, any of the other work, the graphics driver needs to store this. NVIDIA ATI hate this way of doing things. Right? They're all about right now, as fast as possible. This puts extra latency inside of the system, because you have to punch up all this stuff.
Is storing the stuff the reason that you can retrieve model data from OpenGL?
Unfortunately, no. It's not that robust. So all we really do is store all the triangles that were inside of there, figure out, what triangles go inside of a tile, and then basically run it in media mode now that we really want it.
Okay.
So it's actually the simplest hardware way to do it, given our limited space of those things. You still can't go in and say, oh, what triangle did this object belong to? You still need to track that from the application standpoint. Is that kind of what you're asking about?
Yeah, just curious. There's some hooks in OpenGL to export like little WordCraft characters, and I was wondering if that was what they use.
No. Actually, what they probably do at that point is they just throw basically a shim layer for the driver that grabs all the OpenGL files and looks at what geometry was sent. And because World of Warcraft, they probably know the pattern that they issue the models for characters. You can get, right, they're going to do a 7th level orc at this point. And all the geometry and all the textures for this kind of stuff are going to be bound. You're going to put in your vertex array and do the draw. You can fairly well figure out easily what all the geometry is for that stuff. That trick is amazingly useful. Everybody on the planet does it. I mean, I wrote one for the company I worked for because we didn't have anything to run on a graphic board. No one has written OpenGL ES 2.0. So I took games, wrote an OpenGL shim layer, sucked everything out, ran it through the core, found out it really sucked rocks, and we fixed all the bugs, and many of them. But people do this all the time. So, people talk about like encrypting models if you go out and actually buy one. As soon as you run it through a render, game's over. So, learn how to do that. Really simple, really easy, really fun trick. Okay, just because I know I have to wrap up, I have 3 minutes left. Don't worry. Anyways, we require a little more command memory because we have to buffer up everything you asked for. And it introduces a little bit more latency into the system. We have to collect all the data, and then when you do ask for swap buffers, it's at that point we can go off and start doing masterization. So, there's one other benefit of this thing. There's this thing that we call state crashing, which is when somebody does a bad thing of changing state a lot of times inside of an OpenGL application. Not to put too fine a point on it, but you've got a bunch of objects you want to draw. You draw half red, half blue. Hopefully it would make more sense to draw all the red ones first and all the blue ones first, but people lose sight of this when they design their data structures. But it turns out that this is terrible for an OpenGL application. You just keep dashing the pipe, telling you, oh, you need to do all this other changing around. And, things get much worse if you change the texture or whatever. Deferred rendering allows us to actually sort that up and make it a little better, so we can help smooth over the stupidity that most programs actually exhibit when they write code. The problem is people just don't. So, another part that's really nice about this, because we break it up into a tile, and a tile has all the information to be processed, each one can be done completely separately. Does this sound like any algorithm you've heard of before? Ray tracing, right? You do it on a per pixel basis. You fire away from a pixel and you just let it go off. That's why it's embarrassingly powerful. It toss it across 1 trillion processors, and you get a trillion times speed up, minus memory effects. We almost get the same thing. We can drop down multiple rasterizing cores and go off and get embarrassingly powerful speed up. We can double the performance of the core. So, we can do a gigapixel by just tossing down 4 graphics cards. The good news is, and it doesn't actually take anything extra to do it. So if we can make a chip about this big, I could get you a petapixel a second, which would be really great. I'd still need a couple of thousand more power still. But anyways, a couple of other things. There's lots of other optimizations you can do in there. Just like ray tracing, because you have the entire scene, you can look around inside of it, you know all the data, you can reorganize the rendering up to constraints of doing blending and other things like that. But you can have full control over the entire situation and really crank it up quite a bit. So, just a quick review. Do we need power? Yeah, because we minimize bandwidth, absolutely. Sorry, I'm going to go through these quite a bit. Performance, we take a little hit here. There's more latency, but trust me, you'll never know. It adds maybe a millisecond. And for 60 hertz, that's plenty fine. And given the fact that it's on a screen this big, probably okay. And we can always toss down more cores to get a lot better field performance out of the backside. Area, well, yeah, we can chop out most of the frame buffer, so it actually makes the core very small. And because we keep all the graphics on the main CPU, most of these things, the frame buffer is actually in system memory, not on the actual application processor inside your phone. And because of that, we get to do some processing and write it out, and actually it's about as minimal a process as you can get for updating these